In this lecture, we're going to prove some things about regular expressions. Now, before you can really follow this lecture and prove things about regular expressions, it's really, really important that you understand what regular expressions are and how to convert between a set and a regular expression that represents that set. So if you really don't feel 100% on top of the material in the previous lecture, then I urge you to go back and watch that lecture again, just so that you're familiar with what do different regular expressions mean. Because at this point, I'm going to assume that you understand what a particular regular expression represents most of the time. So let's talk about some properties of regular expressions, some things that are always true for regular expressions. So let's suppose R, S, and T are all regular expressions, and they can be any regular expression we want. I mean, you know, R could be the regular expression A plus BC, right? And S could be the regular expression A star. And T could be the regular expression BBCD. Okay? And here's a bunch of properties of these regular expressions. The first one, R plus T is the same as T plus R. So, you know, if we have two regular expressions, they're commutative no matter what order we write them in, they represent the same thing. And that makes sense because remember that this plus symbol really represents union, right? And so if you have, you know, some set 1, and you union that with set 2, well, that's exactly the same as set 2 unioned with set 1, right? And these other properties that I've shown you here are kind of equally straightforward to understand as long as you understand what regular expressions mean. So this says if I take any old regular expression and add that to the empty set, right? That's the same as the empty set added to that regular expression, which is the regular expression. And again, you know, remember that this plus sign here means union. So no matter what set you have, if you take a set 1, and you union it with the empty set, that just equals set 1, right? We have here another property, R plus R equals R, right? If I have two sets, and if I union one set with itself, I just get the set itself back again, right? And this last property just says that no matter what order we union our sets in, we still have the same thing. If this didn't make sense, go back, watch the video about regular expressions again. Now, in your textbook on page 700, you will find a big long list of the properties of regular expressions. And what I've done here, and I have also uploaded to Canvas, so you can download it under this week's materials, is I've created an annotated version of the material on page 700. So the material on page 700 is the material written in black on this page, and the stuff that you can see here in blue is the stuff that I've added. So before you continue with this lecture, what I need you to do is pause the video and download a copy of this, because I'm going to be referring to this as we go through this lecture. But I will just point out briefly that some of the properties that we looked at before, like R plus T equals T plus R, or R plus the empty set is the same as the empty set plus R equals R, these are properties, these are some of the properties that are on this list. So there's just a ton more properties that are properties of regular expressions that are on this list. But now, if you haven't done it already, pause the video and go and download this sheet with the properties of regular expressions from Canvas. Now, we find that these properties are really, really useful because if we believe that all the properties are true, then we can do all sorts of things. We can compare regular expressions and see whether they're equal. For example, if we have this particular property, then we can sort of multiply out and simplify regular expressions, right? And so this says that if we start with one regular expression and then squish it with either s or t, it's the same as saying, well, have the first expression squished with s, unioned with the first expression squished with t, right? So if we union these two and then do the squish, right, or we concatenate the two together, so we concatenate r with the union of s and t, that's really the same as taking the union of r concatenated with s and r concatenated with t. Now, in order to believe that these properties are true, somebody had to prove them. We're not going to go through the whole thing and prove them all by any means, but I just want to convince you that that you could do this, right? So if you have two regular expressions, r and s, if you want to prove that r is the same as s, all you need to do is prove that the language of r, right, that is the set that the regular expression r represents, is exactly the same as the language of s, the set that the regular expression s represents, right? So, for example, if I want to prove that r plus r is the same as r, right, I can start with one side of this. So I need to start either with the left side of this equation, of this equality, or the right side. I'm going to start with the left side, and I'm going to say, if I look at the language of r plus r, that's just equal to the language of r unioned with the language of r, right? Because if you look in the book on page 698 about how we associate our regular expressions with languages, you'll find this definition. But if you union anything with itself, right, so I'm unioning two things that are identical, you just get itself. So we've shown that the left side, right, the left side of this equation, the language of the left side of this equation is equal to the language of the right side of this equation, right? So there's L of left side equals L of right side. So QED, we've proved it. So let's do some example problems from the book. This first one is problem 5 on page 703. And they're asking us to simplify this regular expression, right? And they give us a hint. Keep in mind the properties that are on page 700, that sheet that you downloaded to help us. So here's what we want to simplify. We want to simplify this expression. So let's think about how we can do that. Let's do that step by step, where every single step we're going to justify it with one of those properties from page 700. So here you can see that I, kind of multiplied out, right? I used the distributed 3.1 rule, right, to say, well, AA times B star plus A is actually AAB star plus AAA, and A times AB star plus AA is this thing. So I ended up with this whole thing, and my reason is distributed 3.1. But of course, if you look at the plus 1.3 rule, you can see that if I'm adding, well, here we go, AAB star to AAB star, that just gives me a single AAB star, right? And AAA added to AAA just gives me AAA, so by plus 1.3 I can simplify down to this. Now, I think what we had was pretty good, but maybe you want to change it a little bit. You can also pull out the AA and end up with this expression based on this reason. So now, instead of simplifying a regular expression, we're going to try and prove that these two regular expressions, this big long one, is actually equal to this shorter one. And in fact, we kind of do that by simplifying this guy until we can manipulate it into that form. So I'm going to take this proof a little bit more slowly. I'm going to show you what each step is and ask you to figure out what the justification is. So here's my first line. I say that I can, if I start with this thing, which is the left-hand side, I want to prove the left equals the right. So I need to start with the left and write a proof that ends with the right, or I could start with the right and have a big long proof that ends with the left. Right? But I need to start with one side and go to the other. So I'm going to start with this, and I'm going to say, well, that equals this. So pause the video for a minute, look at this, and try and look at that sheet that you downloaded, and try and figure out what's the reason that I can make this change. And of course, what is it that I did here? Well, I noticed that there's an AA star there and an AA star there, and so I pulled that out using the distributive property 3.1. Here's my next step. Take a look and then pause the video and figure out what rule we should put in here. Right? So what I want you to do is say, how did we get from this piece into that piece, and why are we allowed to do that? And that, I claim, is because of the dot 2.2 rule, right? So dot 2.2 says that lambda times any regular expression is the same as that regular expression. So here's lambda times b plus ab star, and there's that b plus ab star regular expression by itself. Here's the next step in my proof. So again, pause the video, take a look at what I've done. How did I get from there to there? What changes did I make? And can you figure out what the rule is? Well, and I've said it's distributed 3.2, and that's because if we look at this, if we let this lambda piece, if we call that S, and we take that b plus ab star piece and call it R, well, there's the b plus ab star piece again, so there's R again, and we'll call this AA star T, right? Then what we've done is we've gone from SR plus TR up at the top, and we've changed that down here into, what do we got? We got S plus T, right? All times R, right? Because there's our R. And that is indeed distributive property 3.2. And here's the last step in my proof. So take a look, figure out how I made that move, and tell me why I'm allowed to do that. What is the property of regular expressions that allows me to do that? And of course, it's the closure property, closure 5.2, right? If you look at closure 5.2 has a rule that says on the far left, we've got R star equals, and there's a bunch of different things that it equals, but it equals lambda plus R star. Right? So if we say that our R is just the symbol A here, right? Then you can see we've got R star here plus lambda, and down in the bottom we've just converted it to R star. And now we take a look and we say, oh look, I was trying to prove that this left-hand side equals the right side. I started with the left side. Down at the bottom here I have the same thing as the right side. So I'm done. And so at the bottom of my proof I write QED to show I am done my proof. I've completed my proof. Now, I'm not going to say that it is trivial to figure out all of these steps, right? How to you know, I gave you a lot of hints, right? Because I said, all right, well, start here, then move here, and so on. It takes some practice, and part of what you're going to be doing in the problem sets this week is just practicing this kind of work. But before you get to the problem sets, let's do another problem. So this is the problem 6 from the book on page 703. So now we want to prove that this regular expression is equivalent to this other one. Okay, so remember we're trying to prove that the left side equals the right side, so we start with one of those sides at the top of our proof, and hopefully we get the other side down at the bottom. So in this case, we're starting with the left side. And here's my first step. I claim that these two things are equal. So take a look at that sheet you downloaded, figure out what's your reason for that. And of course that's just, if you look, it's just the the first distributive property, distributive 3.1, right? Because all we're doing is we are kind of multiplying through these values, right? Of course, it's not really multiplication, right? Really, we are saying, what does it mean to concatenate A star with this other expression, right? And since that other expression has a union in the middle of it, it turns out that we can do this by the distributed 3.1 rule. I'm going to say it again, it is so very important that you understand what these regular expressions represent, right? So this first regular expression on the left here, what does it say? It says A star. So A star is the set lambda A dot dot dot. And we are concatenating that, right, with the set that contains B unioned with the set that contains AB star. So that's A, comma, AB, comma, ABB, and so on. Right? And so that's what this expression on the left represents, right? Make sure, please go back and watch the previous video again if this isn't really, really obvious to you, okay? Anyway, let's keep going with this problem that we have. I've already finished step one. I've given you a reason for step one. Let me show you what my next step is. So here's the next step I did in my proof. Can you tell me why I'm allowed to do that? Just pause for a minute and look. And of course, if you look at the closure 5.2 rule, we used this one before, right? We know that R star is the same as lambda plus R star, and in this case, just a single A is what we're using for R. So we have taken this little piece right here and expanded it into that. Okay, here's the next step that I used in my proof. Why is that legitimate? And of course, we're just using one of the distributive properties again. Strictly speaking, it's distributed 3.2. As we colloquially say, we are multiplying this out, right? Well, we're not really multiplying it out. We're using the distributive property 3.2. Okay, so take a look. What's the difference between these two lines, and why am I allowed to do that? Pause the video. Figure it out before you go to the next slide. And you can see that the only difference between these two is that I went from A star A here to AA star, and that is indeed what we're allowed to do based on closure 6. So now tell me why I'm allowed to make that jump. Pause the video. And I hope you're kind of getting used to this. Now we're using one of the distributive properties, right? So we have just said, well, I had AA star here times a B, and I had AA star here times a B star, so we could just pull it out and have AA star times B plus B star. So again, think about, how do I make that step? Pause the video, figure out what should my reason be. And of course the reasoning is closure 5.1, right? That we know that if in this case we let R just be the expression B, right? We know that R star is the same as R plus R star. So that's telling us B star is the same as B plus B star. And that makes sense, right? Because if you think about it, what is B star? Well, B star equals lambda B, 2 B's, 3 B's, and so on. And if I union B star, right, and I add that, a union to B, well, B's already in there, so unioning this B star with the set that just contains B will just result in the same old B star. And I'm taking things really, really slowly here, so I've moved from that step to that step. Can you tell me what reason lets me do that? And of course the answer is just the dot 2.3 rule. It's just the rule of operations for concatenation. And finally, magic. Look, I started with the left-hand side. I ended with the right-hand side. So I've proven it. They are the same, QED. And you always want to remember to write QED down there. Okay, let's try another kind of problem now. Let's find a regular expression for a language that is over the alphabet AB, right? So A and B are the symbols we can use, in which no string contains the substring AAA. Okay? So let's start thinking about how you would make such a string. What a string like this would look like. How would you build this string up, right? What kinds of strings do you have? How can you make one of these strings? Well, if you have a string that is any string over the alphabet AB that doesn't have a AAA, what do you think the beginning of it looks like? Well, I would argue that it could start with a B, or it could start with one A and then have a B, or it could even start with two A's, but by the time we've got two A's, we got to have a B so that we don't end up with that AAA substring. And I'm also going to claim that we can repeat any of these guys as many times as we like, right? So we could have a single B, and then maybe two A's and a B, and then one A and a B, and then two A's and a B, and then another two A's and a B, and then another B, whatever we want. We can repeat it as many times as we like. We can take anything from any of these guys. So that gives us this regular expression here, right? So start with just a B, right? Or one A and then one B, or two A's and then a B. And then concatenate, pick one thing from here, and then if we want, do it again. Pick another thing from here, right? That's what this star represents. Now, is that it? Are we done? Is that what our string looks like? Have we got everything if we just use this stuff here? And the answer is not quite, because one of the things that I hope you'll notice about this regular expression is this regular expression always ends with a B. And that's great for letting us kind of build up these strings that don't have three A's in a row, but we might want to, after we've done this a bunch of times, have an A at the end, or a couple of A's at the end. So that's what I've done here. I've said you can repeat this first part as many times as you want, right? Even 0 times, right? We've got the star, that's 0 or more times. And once you've repeated that as many times as you want to, then concatenate that with one of these three things. Either concatenate it with a lambda, in other words, just end with a B, or maybe end with a single A, or you can end with two A's. So there you go, we did it. Pretty cool, really, right? That's all the strings that are made up of just A's and B's that do not contain the substring AAA.